Alright, so I'll make up for my mistake of not having the recorder on. It's like Fred Flintstone, he always had his thumb in front of the camera lens when he took pictures in the Flintstones cartoon. So anyways, I got a lot of stuff here. So this was originally, but I made it even better. But I was putting in this fancy thing here. But yeah, so let's take a look here. So you might remember this from class time. So the wavelengths you write in, and these are actually in nanometers, which is 10 to the minus 12. No, 10 to the minus 9. 10 to the minus 12 is picometers, and then 10 to the minus 15 is femto. And then we can get frequency by using 3 times 10 to the 8th meters per second. And we just have to remember that, though being in nanometers, we have to we have to convert it to meters with this 1 times 10 to the minus 9. So now we have frequencies for each of the wavelengths. And then the other data was the stopping potential. And then when you multiply that by the elementary charge, you get the energy in joules, 1.6 times 10 to the negative 19. And of course, a voltage is simply, if it's an electron, we know, if we know it's an electron or a proton, unit charge, or elementary charge, then if we just multiply them together, we get EV. It's volts times 1. And so that's electron volts. But the point is, as we discussed in class, we want this thing to be all in joules. So convert that to hertz, cycles per second. And the energy of the electrons, it's the Ke max, by the way. And then just, so we just went over it quickly in class. Energy of the electron in joules will equal the energy of the photon minus the work function, the amount of energy required to pull it out of the material. And then we form our basic slope and y-intercept. And we tried using solver, and it didn't work. And of course it didn't work because we're trying to put in such ridiculously small numbers and also so many decimal places, right? So if you know anything about computers, there's floating point and then double precision, and so there's no way in the world Excel would have been able to do this. I mean, there may have been ways to get around it, but ways of telling it the format of numbers, but I did a brute force way where I took each of these here and multiplied by, I divided by 10 to the 14th. So that meant that all these become simple numbers with the times 10 to the 0 power. And then in the case of energies, I multiplied them all by 10 to the minus 19. Actually, I would divide by 10 to the minus 19, which is the same as multiplying by 10 to the 19th. So we got the similar thing, and then I did my fit equation, but now with these fit parameters. And so, I mean, it's a little bit on the quick and dirty side, but since I divided by 10 to the minus 19, and I've divided by 10 to the 14th, and I have to multiply whatever comes out of this by 10 to the minus 33. And lo and behold, we get that right exponent. And then this one is 10 to the minus 19. And so I now put it into the solver, and it worked. And let's just notice this. If I do this, I make that a 6. And so now we go to solver. Come on, where are you? Data menu. Solver. And let's just double check. Yep. And the fit parameter is X. Yep. And uncheck that box. We told it to min, right? Okay. Bingo. And the cool thing is that I can copy paste these into here. And now here, like, I just realized I can be uber clever. Watch this. Equals this. And equals this one here. Then watch, I can have this thing. Both graphs will change now, huh? Clever me, huh? And make this 2 for the fun of it. Oh, look at that. It got pretty close, but so, you know, it's tough, right? That's a pretty small sum of the residual squared already. But now I can solve it, and it redoes those numbers. And it automatically did this, and you see that's gone down to 10 to the minus 41. That's pretty damn good. Okay, so photoelectric effect done. I'm going to stop this and post it and get going on another one.